Hi everyone, welcome to Chapter 2, Section 1. So today we're still looking at data, but specifically being able to describe the location within a data set. So looking at like the individual data points and how they compare with the rest of the data points. So the first vocabulary word that I want to talk about is percentiles. You've probably heard about this before. It shows up on your transcripts. So it does show like what percentile you are. And a percentile is just basically saying like what percent of the data is below you. So if you fall within like the 95th percentile, that means there's like 95% of the data below you. So out of all the other classmates that you have, all the other people in your class, that percent is who you're doing better than, which is good. So a higher number is better, lower number is worse. So like 0th percentile means that there's 0% of data below you, which means you are the worst. But yeah. Also, we can also talk about 100th percentile, because 100th percentile means that it's 100% of the data below you, which actually doesn't make sense because your score would have to be part of that 100%. So we can actually never say that there's a 100th percentile. So the maximum percentile you could reach is like 99.99 percentile. So let's do an example with finding percentiles. So here we have an example of a stem plot. It shows the number of wins for each of the 30 Major League Baseball teams in 2012. Reading this stem plot, it is a split stem plot because we have like doubles of the stems. So 6 line 1 would just equal a team with 61 wins. So we've got 30 teams here and how many total games that they won in that season. So the first thing I want to do is to be able to find the percentile for the Minnesota Twins, who won 66 games. So if you look at the stem plot, 66 is this number right here. So that's the Minnesota Twins. So to find their percentile, we want to know what percent of data was below them. So the ones that are below them is the 55, the 61, and the 64. So there are 3 data points that are below them, which means out of the 30 data points in total, that would make this 10% is below them. So that means the Minnesota Twins who won 66 games was the 10th percentile, because 10% of the data fall below their score. Next, I want to be able to find the percentile for the Washington Nationals, and they actually scored the most. They won 98 games. So because they were the high score, that means there are 29 data points below them. So 29 out of 30. To find that percent, dividing that, we get 96.67%. So when we deal with decimals, for percentiles, we usually round normally. So because this is a 0.67, this would round up to the 97th percentile. So if it was like 96.1, then it would just be the 96th percentile. So round normally with your percentiles, because we usually want to keep it at whole numbers. Okay, and then let's do one more example. So for this one, I want to find the percentile for the 2 teams with 93 wins. So as you can see in the data set, there's 2 different 93s. So because of that, we basically only count the ones that are below both of them. So that would be 22 teams below them. So there are 22 data points that's below 93, so from 90 downwards. So then dividing that by 30 of the total, that gives us 73.33%. So that would be the 73rd percentile. Okay. So now that we know how to find percentiles, let's try to make a graph so that we can visually see what percentiles look like. When we make graphs using percentiles, this is called an ogive. So it's spelled kind of funny because it kind of looks like ogives, but it's actually pronounced ogives. Okay, so using my same data, I'm looking at the a table that'll kind of help me figure out for each data point what percent, what their frequency and relative frequency, and then their cumulative relative frequency is what we're looking for at the end. So I kind of just split this up by the stems that we had. It just makes our graph a little bit easier, so we're not looking at like individual data points yet. So first I'm going to fill in the frequency table. So I know between 55 to 60 there was just that one number, the 55 that we had in our stem plot, so frequency of 1. And then from 60 to 65, that's our second row, so frequency of 2, and then 4. I'm just going to fill in the rest real quick. Okay, so our relative frequency, remember, that's our percents. So we had total data 30 data points total. So to find our relative frequency, we're just dividing each of our frequencies by 30. Okay, so I've just gone ahead and calculated all the relative frequencies. So the next thing we want to look at is cumulative frequency. Cumulative frequency just means we're going to keep adding, as for each row, we're just going to keep adding what was before it. So that's why it's cumulative, and we're looking at the frequency column. So for cumulative frequency, we always start off with the frequency we started with, so which was 1. Then for the next row, we're adding the 1 that we had with the 2. So now cumulatively, basically from 55 all the way up to 65, not including the 65, there have been 3 occurrences of this. And then we keep adding, so adding the 4 to my cumulative frequency of 3, and then adding the 3 to the cumulative frequency of 7. And by the end, you should end up with the total amount of data points that you had, which was 30. Okay, cumulative relative frequency is pretty much the same, just this time we're looking at the relative frequency instead. So we start with our 3.3%, and then we keep adding to that. So 3.3 plus the 6.7 gives us 11%, and so on. Okay, so I've gone ahead and added up all my, oh my goodness, sorry guys. All my relative frequencies. And so as you can see, because of rounding error, I ended up with 101% at the end, which is obviously, that doesn't make sense. So I wanted to show you this because if you just add up the relative frequencies, yes, you're doing things correctly, but sometimes you get the rounding error, so I just wanted to show you that. Really what you can do is, looking at just the cumulative frequencies, you know that the cumulative frequency, you're going to divide by 30 to get to the cumulative relative frequency. So really, our rounding error started right here in the second row, because 3 divided by 30 should really be 10%, and we've already got rounding error right there. And so that just continued on after that. So just know it's supposed to end at 100%, because 30 out of 30 is 100%. But for the sake of this example, I'm just going to continue with these numbers since I've already got them here, and then I'm going to make the graph with this now. Okay, so I've set up my graph on the right here, and so how we plot things out is we start with our lowest number, which was 55. And then because we're talking about our cumulative relative frequency on our y-axis, then what at the point, data point 55, there's nothing below it. So 0% is below it. So our first point always starts off on 0. Then at 60, that's when we have 1 cumulative frequency below it. And so that ended up as 3.3%. So our next point will be at our first cumulative relative frequency. And so that's like the weird, tricky part for this. But otherwise, as long as you remember to start at 0 and then graph the rest of your cumulative relative frequencies at the next points, then you're good. So the next one was 11, 24 point something, 34 point something, and so on. So I've plotted out all the points for our cumulative relative frequencies, and then we're just going to connect all of them with a line. Okay, here's our graph. To interpret this, we kind of want to look at how steep our curve is as we talk about like whether the graph is skewed left, skewed right, or symmetric. So basically, the steeper each of the segments are, so like right here we have a kind of steeper segment between 90 to 95. And that makes sense because if we look back at our stem plot, that's where we had the most values or the most data points between 90 and 95. And so it gets steeper when there's more. So that's kind of how you can tell whether something is skewed or not. And so if you look at our overall stem plot from before, it was kind of skewed more towards the left because we have fewer of the lower numbers. And so looking at our ogive, it's less steep towards the left and then more steep towards the right. So that's how we can kind of tell that it's going to be skewed left. So in addition to percentiles, we can also use something called z-scores to measure position within a distribution. So z-scores is just like a standardized way to measure how far each data point is away from the mean. So mean is always our reference point, and so we're not really talking about the spread anymore. It's like the actual position in relation to the other data points. So whatever measurement you were actually looking at for your data, whether like for us this was like how many wins, or if you're talking about like height of a population or something, so how many inches, whatever unit of measurement you're using for your data collection, it doesn't matter when we're dealing with z-scores. It's like the standardized, it like makes it the same for no matter what type of data set you have. So we're going to use the standard deviation itself as like a unit of measurement of distance away from the mean. And so the z-score formula, so that we can convert all of our data points into this standardized way of measuring, is z equals, I'm going to use x to stand for our data point, minus the mean divided by the standard deviation. So let's label some things. So x was our data point. This symbol here, it's a mu. Looks like a m, looks like a u, read as mu. So it stands for the mean. And then this is the Greek letter sigma. It's like an O with a hat. It stands for standard deviation. So that's our formula for the z-score. So that's why it's z equals. So basically, we can, once we know the mean and the standard deviation, we can calculate the z-score for anything. So let me give you a few examples of what a z-score could mean. So let's say we had a z-score of 1.5. So whatever your data set is about, let's say the mean was at, like for this example here, we have the wins from each team of baseball, whatever. The mean is 81 and a standard deviation of 11.93 that I calculated really quick. So if that were the case for our set of data, having a z-score of 1.5 would mean that whatever team scores, that team score would be 1.5 standard deviations above the mean. So like if the mean was 81 and a standard deviation was 11.93, that means they're 81 plus 1.5 times the 11.93 distance away from 81. So let's say I think one of the teams was like the Minnesota Twins or something, had 66 wins. So their z-score would be 66 minus the mean of 81 divided by the standard deviation of 11.93. So when you do that, you end up getting negative 1.26. So that would mean that the Minnesota Twins, their amount of wins that they had was 1.26 standard deviations below the mean. So they scored less than average because the average was 81. And specifically that distance of 1.26 standard deviations below the mean. So if you were closer to the mean, then your z-score would be closer to 0. Because if you are exactly the mean, so let's say like this team right here scored 81. I don't know what team that is. But if they scored 81, then when you do the z-score formula, you would have the x value of 81 minus the mean of 81 divided by the standard deviation gives you 0. So if you are exactly the mean, or like if your score was exactly the mean, then your z-score would be 0 because you are 0 standard deviations away from the mean because you fall exactly on the mean. All right, so one thing that we do have to do in this class is interpret a lot of things because we want to be able to effectively communicate to people like what do these numbers mean? So when we find a z-score, if you're ever asked to interpret a z-score, it follow the same format every time basically. So I've written it down here. Like whatever your x value is, so if we were talking about the Minnesota Twins 66 win number, then the Minnesota Twins score of 66 is 1.26 standard deviations. Oops, I forgot to read that. Standard deviations below the mean of 81, because that was the mean of the whole thing. And it was below because of the negative number. So that's how you're going to tell. If you get a positive z-score, that means you're above the mean because your score is higher than 81, and so on. So that's how you want to interpret it. Okay, the last thing for this section that I want to talk about is transforming data. So if we had our data set, I'm still going to use this baseball example, but let's say we had to do something to every single data point. So either like add every single data point by 5 or something, or even if we multiplied every single data point by 2, something like that. So for whatever reason, if like they gave out freebie points for baseball, I don't know, however that works. But if for some reason your data set all had to be either added or subtracted by something, multiplied, divided by something, what would happen to your overall distribution? So I'm going to give you an example. If we're using the same data set as before, I'm going to add every single data point by 5. And then I want us to look at socks for it. So the center, the shape, all that good stuff. So I've recreated the stem plot, but this time with every data point, I added it by 5. So the 55 that we started with became 60. So you can see that here. And then the 61 became 66, 64 became 69, and so on. So as you can see, the shape of the stem plot is basically the same. Just the numbers changed, the individual values changed, but the shape kind of just shifted downwards a little bit. So I guess to the right if we're making like a graph on the x-axis. And so now our biggest number is 103 instead of 98. Our smallest number is now 60 instead of 55, but everything just shifted by 5 basically. So when that happens, if we were to find the mean of this data set now, surprisingly, I don't know if it's a surprise to you, the mean is now 86. So it increased by 5. Which kind of makes sense. If you add 5 to everything and then divide it back out by how many there were, the mean, the average should now be just 5 more because you kind of consistently changed it for every data point. And then the standard deviation, if you calculate that now, actually is still 11.93. So if you think about it, standard deviation is talking about the spread. It's when you added 5 to everything, it's not like you changed the range or anything. When you, your biggest number increased by 5, your smallest number also increased by 5. So the distance between them is still the same when we talk about range in terms of spread. So the standard deviation then doesn't change at all either, because you haven't changed how far apart the points are in relation to each other. So when you add by something, the mean changes, standard deviation does not. So as a summary, if you add or subtract every data point by a constant, so this works for both adding and subtracting, the shape's not going to change because if you look at the graphs, same thing. Outliers, it's not like we gained any outliers, so that doesn't change. The center does change because it increases/decreases if you're subtracting by a constant, by whatever the constant number is. The spread doesn't change. Okay, let's take a look at transforming data if we multiplied or divided now. So let me make a new distribution of the same data set, but this time we're going to multiply everything by 2. Okay, so I took the time to make a new stem plot. So what I did was took every single data point and I left it the original set here on the right. So this was the original data set. I multiplied every number by 2 and it turned into this as my stem plot. So as you can see, the stem plot kind of stretched out a little bit more. So it sounds like the spread definitely changed here. So first of all our numbers are now double. So because of that, the spread between each of our stems also changed a little bit. So the range is a lot greater. And here, if we calculate the new mean and standard deviation, the mean now actually becomes 162. Interesting. So if we multiply everything by 2, then our mean also gets multiplied by 2. Okay, so it makes sense. If you multiply every single data set by 2 and then you add them all together, divide by how many there are, it makes sense that the average would also get multiplied by 2. Now, looking at our standard deviation, I calculated this in my graphing calculator, and as you can see, right here, standard deviation is 23.86. So I've added that to my notes here. So our original standard deviation was 11.93. So it basically looks like if we double 11.93, then we get our new standard deviation as well. So in this case, whenever we multiply or divide by something, by a constant to our data set, then the mean and the standard deviation also get multiplied or divided. Divided also works because when you multiply by something, you're really, or when you're dividing by something, you're really multiplying by the reciprocal. So it makes sense. Okay. In general, we have that for socks. The shape still doesn't change. If you look between our new stem plot with our old one, the shape itself, like, it's still slightly skewed towards the left. That hasn't changed. It just got spread out more, but the general shape itself didn't change. Outliers doesn't change, but our center and spread both get multiplied by the constant. So one last example related to transforming data. Let's say in 2010, taxi cabs in New York City, they charge an initial fee of $2.50 and then $2 a mile for however far you go. So in equation form, it looks like your fare equals 2.5 plus 2 times however many miles you travel. At the end of the month, a businessman collects all his taxi receipts and calculates some numerical summaries. Turns out that the mean fare that he paid was $15.45 with a standard deviation of $10.20. So what are the mean and standard deviation of the lengths of his cab rides in miles? So we're kind of like working backwards here because we know what the mean and standard deviation are in terms of the fare, but we're trying to figure out the mean and standard deviation of miles. So we can kind of work this equation backwards to solve for miles instead. So if I subtract both sides by 250 and then divide both sides by 2, I would get that the miles is equal to your whatever the fare was minus 250 divided by 2. We're basically saying we're transforming all of his data points, all of the fares that he paid. If we subtract by 250, divide by 2, that'll calculate the miles for every single receipt that he has. So if this was the case, then we're basically transforming the entire data set by subtracting 250 from every data point and dividing by 2. So using the rules of what we know between adding and subtracting and multiplying and dividing, our new mean and standard deviation are going to change accordingly. So earlier we said that for the mean, it changes whenever you add or subtract, and it also changes whenever you multiply or divide. So in this case, that means our mean, if we started out with a mean of $15.45, this will have to get subtracted by 250. And then we'd have to divide by the 2 to get our new mean because our transformation involved subtracting and dividing. When you do that, you end up with $12.95 miles, because now we're in terms of miles after transforming like that. Okay, for our standard deviation, earlier we said standard deviation only changes when you multiply or divide. So in our transformation, we subtracted by 250, which wouldn't change the standard deviation at all, since spread doesn't change when you add or subtract by a constant, but it'll change when you divide by 2. So our original standard deviation of $10.20 will also get divided by 2. Oops. Sorry, not a dollar amount anymore. So when you divide by 2, you get 5.10. And so now it's in terms of miles. So that's how you would transform a mean and standard deviation even without the full data set, or without having to do all the transformations to every single point in the data set. Okay, that's it for section 1. Thanks for watching. Bye.